Hey students, I got a question about number 53 in chapter 40, and I looked it up. This is a pretty challenging one, and challenging for two reasons. One is the conceptual physics, and that's really what I want to spend a lot of time talking about and make sure I get that across to you. And then the other one is just understanding the question and converting the question into math and then doing the math. So I can see why the author gave it the highest rating, a magenta color here, because this is a pretty a challenging one here, and it's deserves some time here. So this might take a little while here, but let's run through it. Let's talk about first the problem, and let's try to understand the problem first here. It says here that a woman on a ladder dropped small pellets towards a point target on the floor. Show that according to the uncertainty principle, the averaged missed distance between them must be at least, in other words, there's some unknown position of where it lands, where of course m is the mass of the pellet, h is the initial height of each pellet above the floor. You can assume that the spread, the impact point, is given by this. Let's talk about that equation. And then they give us some numbers to calculate this out here. But this is a really good opportunity, I think, to kind of digest a little bit better the uncertainty principle, because this is our goal here, is to learn modern physics. And there was no such thing as an uncertainty principle in classical physics. So this is a whole new phenomenon, and it's a little difficult to understand because I don't have anything in the classical sense to compare it. So let me start in a classical sense. Let's say this is the floor, and let's say this is the target. And if you'll notice here, they said it's a point target. So it's a little tiny point, and you're trying to hit it. And in classical physics, you would come up here, and you would hold it maybe right here, and let it go, and gravity would pull it straight down, and in this case, you would miss. So you missed your target. And of course, you missed the target because you didn't put it in the right position to begin with. And so to actually hit the target, I guess you would put it right about there. And so you would hold it there above the target so you know its position. And you carefully, very carefully, make sure you don't give it any sideways motion. You let it go, and so it falls straight down and hits your target. So in order to hit this point target, in classical physics, we would need to know very accurately what is its position. And we would figure out its position very accurately, and at the same time, very accurately know its left and right velocity, or you might say its left and right momentum. And say, all right, what is its momentum? And like I just said, we would have to know this very accurately, and this very accurately, in the sense that we'd have to say it is 0. Well, that's where the whole lesson comes into play. Surprisingly, and let me not lecture to that on now, but looking at Heisenberg's thinking and the property of waves, we argued, and your book argued here, that there is a balance that has to go on, since the position is really kind of the length of the wave train, and then the momentum is the wavelength. To get a single wavelength, it's got to stretch out. Oh, I said I wasn't going to lecture on this. Okay, well, maybe just a moment. But a single wavelength would give us a well-defined momentum, but see, it would continue really far, so it would give us a poorly defined position. On the other hand, something that was a wave packet would have a position known where the waves begin and the waves end. So here we have a little more well-defined position. Where is the say electron, but treating it as a wave, so where are the waves? But then to make a packet like this, it's got to be made out of a bunch of different wavelengths. And a bunch of wavelengths means that its momentum, which depends on wavelength, would vary. So we know its position a little better, but we don't know its momentum. So there was a trade-off. And so we went through the logic on this, and we came up with the Heisenberg uncertainty principle that says there's always going to be some unknownness in its position. And so that's kind of the length of the wave train. Where does the electron begin and where does it end? So we don't know this number. And then, of course, because there is a beginning and an end, it has to be made out of multiple wavelengths, which means we don't have a well-defined momentum. But see, the longer this is spread out, so in other words, the bigger this is, the smaller that can be. So the product of these two, we argued, always has to be less than or equal to h bar, which is Planck's constant divided by 2 pi. We call that the reduced Planck constant divided by 2. So this is the uncertainty principle, and that's why I want to take the beginning time of this problem and just kind of point out the uncertainty principle. This kind of thing did not exist in classical physics. That's why I was saying if you were just going to drop these, you would say, I know its position really well. And so this uncertainty is nearly zero. And I got to have zero momentum left and right, so 0. And that clearly is not bigger than some number. Now, this is a small number, granted. I mean, this is really h over 4 pi, which h is, 6.63 times 10 to the minus 34. And I guess units are joule times second, and then 4 pi. So the reduced Planck's constant is granted a small number, but it is not 0. And so for things that have big sizes or masses, we could say we really almost have 0. And so this is why classical physics works. But when you get down to small things like electrons, we run into troubles with this, which I think is the whole reason why your author not only asks you in part A to find out what that uncertainty is, but then in part B gives you some numbers so we can actually calculate it and begin to see that the uncertainty in the position is incredibly small, and it's something that you would never notice for something that's even as big as a half a gram dropped from a height of 2 meters. So looking forward to part B and actually getting some numbers here. All right, so keeping that in mind, let me come over here and rethink about this problem with an uncertainty in it. So if I kind of make the floor again and say, here's my target, and I'll say, all right, I begin somewhere up here, and I'll just kind of make maybe I'll make a color here. But I'm going to have to say that I'm going to drop it from some point. But I can't really know the exact position of it. This is where the uncertainty principle comes in. Remember, I don't know. I have to have some number here. This can't be 0. Okay, there's got to be some uncertainty. I'm not completely sure where the electron is on the x-axis. Well, maybe I should have put momentum in the x direction. So that maybe to represent it, I'll just kind of color in a certain length and call this then delta x. And maybe I'll call it initial because that's before I drop it. I would say, where is this electron? So there's some uncertainty to it. Now, again, if you kind of understand the meaning of this, this is kind of the play of numbers we're going to have to go through. In one sense, I want this number small. See, because when it's small, then it's going to start off with a lower uncertainty, and when I drop it, that's going to result down here in an uncertainty that is hopefully small. But see, here's the interesting thing about it. If I make this number small, it makes this number big. That means I don't know its momentum. Also, it means that I can't make the sideways momentum 0 like I was talking about here in the classical problem. It's got to move left or right a little bit. And I would want that to be small. And to get that small, I would want this big. So half of me is saying, make this big so that it won't move left and right as it's falling. But of course, if this is big, it could be falling from any place. And so the uncertainty when it hits the ground has got to be at least as big as the uncertainty where it starts. So that's telling me I don't want that big. But if I don't want that big, then I get a lot of uncertainty in the momentum. And so as it falls, it spreads out. So I still get a big uncertainty. And so this is kind of the beauty of the problem, realizing that there is some probably optimization. This is really an optimization problem. Some uncertainty here at the beginning that if I make it too big, well, then I have the advantage of this getting small, but I still have a big uncertainty when it hits the ground. On the other hand, if I make this uncertainty too small, which, at first I'm kind of liking, and in terms of classical physics, that's all I would want to do. But with the quantum aspect of this Heisenberg uncertainty principle, if I make that small, I don't know the momentum in the x direction. And so making this small is great at the beginning, but then because it has a sideways momentum, a sideways motion, by the time it falls and gets down to the ground, it has a big uncertainty down here. So I don't want that to be too small. So there is some kind of balancing effect, and that's why the sentence here, I think, now makes more sense. It says, show that according to the uncertainty principle, the missed distance must be at least this big. So what I'm saying here is there's some uncertainty here down at the bottom that is got to be a little bit bigger than the uncertainty at the top, because I have an uncertainty at the top, which then means I have some uncertainty in the momentum. So by the time it falls, it spreads out. And so let's call this the uncertainty at the bottom, final. And this problem is saying that this uncertainty at the bottom, x final, has to be at least this big. Could be bigger, but this is the smallest. And so, like I said, we're looking then for this problem as an optimization of how can I make this the smallest? Well, there's some size here that, again, if I make this thing small, because of the uncertainty principle, this smallness that I start means it starts with a high uncertainty in its momentum, and so as it drops, it spreads out. So I don't want that too small. So in other words, as I start to make my uncertainty in the position bigger, the uncertainty in the bottom gets smaller and smaller and smaller, up to some point, though, because then, if I get this uncertainty here, as I said earlier, just from the classical nature of it, if I don't know where it is to begin with, I certainly don't know where it is when it lands. So this one here is always going to be at least as big as that one. So if I make this too big, then it becomes big again. So there is some kind of minimalization in here. And that's what I'm going to be hunting for. Okay? And that's really where I wanted to start this. I hope I didn't talk too long, the first 13 minutes here, but trying to really understand the problem of what I need to do. And so I need to incorporate the idea of a function that I need to minimize. So it sounds like I'm going to look for a function and I'm going to take its derivative and set it equal to 0 because I got to minimize that function. It's an optimization problem. And I'm going to do that with the uncertainty principle. Okay, so if all those words make sense to you, let's put those words into mathematics and see what we get. All right, so I would say this. I would say that the uncertainty when it lands would be equal to the uncertainty where it begins plus, I'm just going to put a little box here, the additional uncertainty as it falls. And as I said earlier, conceptually, that uncertainty is created because I have an uncertainty in the x momentum, the sideways momentum, as it is dropping down. Okay? So this piece right here is the growth, and that's what I'm trying to say. So the uncertainty at the bottom has to be equal at least to the uncertainty. That is, if you just think about classical physics, if you don't know where you are when you drop it, you could be here and it would go straight down. Or you could be here and it would go straight down, or it would be here, it would straight go down. So just from classical physics, we would say that the uncertainty where it lands is equal to the uncertainty where it begins, okay? And in classical physics, you would want to minimize that to minimize that. And you could then say you're going to hit a point because you're going to start at a point. So you can do that in classical physics. But as we talked about, there is going to be a spread, a growth, if you will, because of the sideways momentum, which has to do with how small the uncertainty is where you began, and it's going to spread out. So I'm going to say that this second line, the growth part right here, would really be the uncertainty in the x velocity when I let it go, I'll say initial, multiplied by how much time does it take then to drop. And maybe for starters, I'll do the easy one, the time to drop. So the time to drop just takes us really back to physics 121 and the whole conservation of energy. I'll just say initial energy equals the final energy. And if you start something up a height h, you would then say it starts with a potential energy as mgh. And of course, as it falls, sorry, head down the wrong road. I want to get time, and energy has nothing to do with time. That's my bad. I had these distances in my head, but they're x distances, not y distances. Sorry. I guess the one I want, going back again to physics 121, is the equation when you drop something, we have y equals y initial plus the initial velocity in the y direction times time plus 1/2 a in the y direction t squared. Okay. And this problem could be even harder than I think the author's intent, because I'm going to go ahead and simplify and change this to saying we're going to drop it kind of in a violation of what he's really after in this point by saying the initial velocity in the y direction is 0. And that has to do with the uncertainty in the y direction. So we could have the same discussion about an uncertainty in the y direction. But as we're going to see, and we're going to argue here, that that's such a small number, it really doesn't change this by too much. But that is an additional factor. And so if you'll let me kind of skim over that, and so this author is treating it as an uncertainty only in the x, I'm going to then argue here that it has very, very little, especially since we're dropping it 2 meters. I can ignore the starting speed and say then that the vertical height is h, bring the 2 over to here, divide by the acceleration, which is g, since we're dropping it, then taking the square root of it, I can roughly argue here that this is the time. Like I said, there probably really need to be a little bit of uncertainty in the vertical motion, and I'm going to just argue that that's so small we'll skip over it. But I see in his answer, remember he's trying to make it look like this, there is no factor here with the uncertainty in the y direction that it starts. So I can tell that the author's ignoring that. A little bit in violation of the intent of his problem, but this is hard enough in of itself. And that vertical one is something we usually save for an upper division class here. So that's the factor, though, that I see, the 2h over g. Now, it's raised to a factor of 1/4, which is kind of interesting because what I got right now is raised to a power of 1/2. So something interesting has to happen here with the mathematics. Probably some kind of square root to get that thing to come in to be 1/4. But let me not try to reverse engineering it. Let me just move forward and see if I can come up with that. All right, so if I use that back in this equation, and I'll just move down here, and I think this is going to end up being a long problem, so let me put number 1 up there. Let me then say, okay, so the uncertainty would be this. I'd have the uncertainty that it starts with plus an unknown velocity initially in the x direction, and then the time it takes for it to drop down is my whole argument of why this thing's going to spread. And so this is a 2h over g to the 1/2 power. Okay. All right, well, let me keep going. Actually, maybe not with that. Let me do that little side trip here. So this is where the uncertainty principle comes in. So if we are trying to look for this velocity in the x direction that it begins with, maybe I'll write it by saying the uncertainty in the x position initially times the uncertainty of the momentum in the x direction initially has to be greater than or equal to h bar over 2, which, by the way, looking at what we're hunting for, you can see the h bar over here. So here's our reduced Planck's constant. So that's good. Okay. And this square root thing. All right, so hopefully something's going to come out of this here. Now, maybe I'll do this, that momentum, remember, is mv. So I could probably write this as the uncertainty initial in the x direction times the mass of the pellet we're dropping times the uncertainty in the x direction initial has to be greater than or equal to h bar over 2. So there's what I'm trying to hunt for here. I'm trying to say, what is that? I'm going to put it in there. All right, so this would be the uncertainty in the speed in the x direction has to be at least greater than or equal to, and it looks like I'll have an h bar and a 2m and an uncertainty in the x direction. Okay, and maybe we should, again, just talk about this equation. So here's page 2. Because this equation hopefully is kind of filling in the conceptual idea. See, if your uncertainty that you begin with is small, you're going to have a big uncertainty in the sideways velocity of it. That's why I had said many times, and say it one more time, that if you make this uncertainty too small, if you try to locate where these are, sure, you've got them figured out where they are, but you don't really know their sideways speed. So once you let go of it, it has a huge sideways speed. And so as it takes the time to drop, it ends up with who knows where it is. You might draw it in terms of a diagram like this. If we dropped it from that spot, because it has sideways motion, it can end up as far as this way or as far as that way. Now, if we dropped it in the middle, it could go to here to here. And if we dropped it from this edge, because again of its sideways motion, it might land anywhere from here to there. And so maybe that little spread kind of helps out the picture of why the uncertainty in the final position is going to be a little bit more than what it starts at. And that's what this math is all saying. The uncertainty in the final position is the uncertainty where it begins with plus how much it spreads. Okay, and so this extra piece is, half of it is really this spread here, and the other half is this spread there. That's this piece. All right, so now I have this number. So now let me use it back where I need it. And again, keep in mind, I'm trying to find the minimum, so let me just set this to an E quality. Okay, see, the best I can do is it would be equal. It could be more than that, but we're trying to make this as small as possible. See, that's the goal here. Show that according to the uncertainty principle, the average missed distance must be at least. Okay, so I'm trying to make it the smallest I can, but note it can't be 0. So there's this at least. It must be at least this big. All right, so I'm going to set that equal to 0 and then continue on with my mathematics here. So delta x final equals, so first write that one, delta x initial plus. Okay, so the uncertainty in the velocity must be this h bar over 2m delta xi. and then a 2hg to a 1/2 power. Which, by the way, keeping in mind where we're trying to head, I kind of like what I see here. I have a 2 and h prime over m. Now it's to a 1/2 power. I don't have that. I have what you might say to a 1 power. But remember, if somewhere along the line, for whatever reason, I don't know yet, I have it taking a square root, I would get a 1/2 and I'd get a 1/4 there. And that's what both of these are. So thinking somewhere in here there's a square root coming or something. So that would kind of get me to this pattern. But I got what I wanted way back when I first explained. I'm trying to get an equation that would tell me what the uncertainty is at the bottom based upon the uncertainty at the top so I can optimize it. And now I'm there, right? I have an equation that says what is the uncertainty when it lands based upon the uncertainty when it begins. And now you can see the both pieces. You can see the piece from classical physics and you can see the piece from the quantum physics. In fact, if you just made a mental picture of what this would be, if you plotted what is the uncertainty when it lands compared to the uncertainty where it begins, remember in classical physics, we don't have this term. In classical physics, we can know its position exactly and it falls straight down. So whatever we don't know in its uncertainty at the top results in the same uncertainty in the bottom. And that's what this term is. And on a graph, that would be a line at 45 degrees. And so if we only were doing classical physics, we would say, well, the uncertainty at the top is the same. The top is the same as uncertainty at the bottom. So at the top, if it's 0, then at the bottom it's 0. But if at the top you don't know it for, say, 0.5 millimeter, well, then at the bottom you don't know it for 0.5 millimeter. And if you look carefully at this equation, you can see that if the uncertainty at the top is pretty big, you can kind of ignore that. And then we just have the uncertainty at the beginning equal the uncertainty at the bottom. The quantum mechanics falls away. And so this number can fall away. Actually, I should probably point out that in classical physics, usually our things have so much mass that this number is so small that we never noticed this until we got into, what our discussion is now, a discussion on modern physics. But if you have something where it has a small mass, and that small object, because it has a small mass, you're trying to locate in a small position, like an atom, you've got both of these that are small, this can actually then dominate this, or at least be in comparison. And so you can't just ignore it. And so this is the quantum effect, an effect that, again, we would never have even thought about in terms of classical physics. Anyways, I kind of got off of my graph. Let me go back to my graph here. What I'm trying to say here is then for big delta x's and or big masses, it would just follow this line. But as delta x initial got small, this term here would begin to be noticeable to this, and in fact, eventually would dominate this one, and we can then kind of even ignore that one, and then we would have this 1 over delta x, and so that would be this asymptotic hyperbola. It would kind of match up something like this. So if I were to graph, well, I guess I just did, but a kind of a freehand graph, but if I were to graph this uncertainty, the final uncertainty, as a function of the initial uncertainty, it would look something like this. And this is what I'm hunting for right there. I'm hunting for what is the smallest amount of uncertainty we can have based upon the uncertainty it begins with. And now we can see it in graph form, that if the uncertainty is too small, in other words, if you try to just think in terms of classical physics and you try to take this object like an electron and narrow exactly where it is, as I said, you give it a lot of sideways momentum, and so by the time it falls, you have no clue of where it lands, or very little clue, and that's what this upper part is. That the uncertainty where it lands gets so big because of that sideways momentum. That's the quantum effect. And then, of course, the other one's just the easy, obvious effect that if you don't know where it is when you begin, you don't know where it is when it lands. And that's this one. So I'm hunting for this. So let's see if we can find that. Again, that's the whole question here. What is that? And according to the problem, it should be equal to this number. Okay, so let me optimize this and find its minimum. And I'll do that by taking the derivative of the function as a function of its initial uncertainty and set it equal to 0. That should allow me to solve for what is the value on the horizontal axis, and then I can put that back into the function and find out what that smallest value is. All right, so now it's just a matter of taking a derivative. So I'm going to take a derivative of this function. All right, so the derivative would equal, derivative of this one's easy, that's just a 1 plus, and maybe to make my life a little easier, let me look at where the constants are and pull those out. So let me leave the 1 over x here alone, but this would be this h bar over 2m, okay? Then taking the derivative of this, I like to think of it as raised to a -1 power, but in the numerator. So I'm going to take a derivative of a power. So I'm going to use the calculus of a power function. I'm not going to do the quotient rule. So I'm thinking of this upstairs. So this would be bring down there. That's a -1. Then subtract 1 from the exponent. So that's -2. Although let me move it downstairs. So now it becomes a +2. So there's the derivative of it. Then I have some more constants. So let me just leave those alone. Okay. And so this I will set equal to 0. And then solve for this magical point. This magical point is what should be the size of the uncertainty that I begin with that would get me at this minimum point. So let me find that so I can put it back into my function. And you can, of course, I think, hopefully see that if I move this to the other side, it gets rid of that here. Maybe I shouldn't try to do that in one step. So let me mentally move this to the other side. So that would be an h bar over 2m. Now let me leave this alone for a moment, but mentally move this to the other side. So there's the 2h over g to the 1/2. I say that because when I move this over here mentally, then I can take this in the denominator and multiply it over here by this 1, and so this would be delta x initial quantity squared. And so now I can get what I was hunting for, which is what is the value of the uncertainty to begin with, so that I can put it back into this function to find its value. So, I'm going to take the square root, and that's a good sign, because now I have this to a 1/2 power, and I have the other term to a 1/4 power. And that seems to be in the answer somewhere. So I still don't completely see how I'm going to get there, because once I get this, I got to put it into this function, which has 2 pieces, and this answer certainly doesn't have 2 pieces. So a little nervous, but going to keep going here and figure out, okay, where is this? All right, so now we can find the smallest uncertainty here as we optimize this by putting in the value of x uncertainty initial. So let me put this in that first term. So the first term would be h bar over 2m to the 1/2, and then a 2h over g and a 1/4 plus. And maybe looking at this equation, why don't I just put the h bar over 2m, leave it alone. I'll even put it right next to the 2h over g to the 1/4, because what I'd be left with then is 1 over the x. So 1, see, I might go off the screen there. Let me look. Where am I? 1 over the x. And so this would be h bar over 2m to the 1/2 and 2h over g to the 1/4. All right. And leaving this first term alone, h bar over 2m to the 1/2 and 2h over g to the 1/4. What do I get over here? And you can see that these are the same factors. This is in the numerator, this is in the denominator, this is a half, this has a 1. So when you divide that into here, you get h bar over 2m to a 1/2. And same thing here, that these are the same terms. This is a half, this is a 1/4. So you would end up with the same term, but raised to a 1/4. Now, I think we got it here. You can see that these are like terms. And so they're going to add together. Looks like we have one more page here, page 3. But if I add these two together, I would have 2 h bar over 2m to the 1/2 and 2h over g to the 1/4. Then I guess I'm essentially done, although it doesn't quite look like their answer because, you know, I have a 2 downstairs and a 2 up here. So this does look a little different, but I think what they've done, let me see here, is they've taken the 2 and they first put it inside the square root. So that would, if I did that, let's do that with a green marker. So if I take that 2, put it inside, it becomes a 4. Since the square root of 4 is the 2. And then the 4 divided by 2 leaves you with a 2. Good. I was a little nervous about how mine was going to look a little bit like theirs, because back here when I first got that, h bar over 2m, that factor was just a little different than that one. That had the 2 upstairs and this had it downstairs. But now I see it. So sure enough, took a while to get here, but here it is. And this n would say that this here is the smallest uncertainty you can have when you drop something from a height h. Okay? And of course, part B then says, all right, well, let's actually do some numbers here. Okay? And put those numbers in and see what we get. All right, so I'm going to put a 2. H bar is the h, which is 6.63 times 10 to the negative 34. And the units, well, let me hold off on the units for just a second. But there's the h, and it's reduced, so it is Planck's constant divided by 2 pi. And now we're going to divide by the mass, and here's where my discussion of units better come into play. Maybe I'll put the units down here. Remember, this h here has units of joule times a second, okay? And this is my clue, then, that this h, which has joules, and joules has units of kilograms, I better be careful here. I'm going to check my units, but they give me the mass, but they give it to me in grams. So let me write it as kilograms. So this would be 0.5 times 10 to the minus 3 when I put it in units of kilograms. Now, of course, all of this is raised to a factor of 1/2, so are the units. Okay? And then over here, the height is a 2, and I probably got to watch my units. Let's see. It looks like they gave me height in meters, so that's probably pretty good. I can leave it in meters, especially know that I'm going to divide by g, which I'm going to use the standard 9.8 in meters here. All right, so this would be 2, although the units would be a meter. And then I'm going to divide by a 9.8, which is raised to a power of 1/4. And so this is meters per second squared raised to a power of 1/4. I'll do the numbers. I'm really kind of curious how these units are going to work out. So let's look at this, especially this weird power here. Let's see. A joule is a Newton times a meter, right? So I'm going to think of this as a Newton times a meter. And so I'll take the meter and the second. So the second and the meter. But I'm even going to take the Newton here and write it as a kilogram meter per second squared. Okay, so there's the unit for the Newton. There's the meter, there's the second, and of course I'm dividing it by the kilogram. And this one over here, the meters would cancel, and the second squared would flip up, raised to a power of 1/4. Okay, and maybe I'll just do this, because this would now be seconds to the 1/2 power. Okay, now over here, the kilogram's going to cancel off, and I'm going to get a meters squared, but the square root of that, so there's a meter. And here, one of the seconds is going to cancel, and so downstairs I will get seconds to a 1/2 power. Good. So seconds to the 1/2 power cancels off, and you're left with meters. And so the end result is units in meter, the uncertainty. And it should be. We're talking about an uncertainty based on, and that's a distance. And so using these units, we get the correct units. As you know, if units didn't work out right, it would be obviously wrong. So the units do work out fine. All right, so let's see what kind of number we actually get here. So 2 times Planck's constant, 6.63 times 10 to the negative 34, divided by 0.5 times 10 to the negative 3, divided by a 2, and divided by a pi, and I'll hit enter. And then I need the square roots of that. So this first one is really small, not a surprise. But I'm going to end up multiplying it by this one here. Let me figure out what this one is. The top would be a 4 divided by 9.8. And I am going to raise that to a power of 1/4. So I'll just go 4 reciprocal. Okay? So that's that term. So let's multiply the two together. So let's come up here and grab the first one and go times the second one and hit enter. And we come up with an uncertainty here of 5.19 times 10 to the minus 16th. And so to wrap this up, here's what this is saying. That if we took these small 1/2 gram pellets and dropped them, there is no way we can know the final position any better than this number. This is the best we can do. We could be worse, hopefully, if we took some effort out this and we tried to. This would be the best we could do. But look at that number. an atom is about the size of 10 to the minus 10th. So this right here is 6 more digits smaller. This is 1,000,000 times smaller than the atom. So, in other words, if you drop pellets, you can know its position up to 1/1,000,000th of the size of an atom. 1/1,000,000th. That's pretty accurate for things that you and I would do in an everyday, and that is why this uncertainty principle never really showed up until we got into small things. That's why that graph I kept showing you that looks like this, that is if I did a plot of things with size and velocities, and we kind of set up an absolute speed at the speed of light and kind of divided it, we could put all of our classical physics up here and say anything that's big and slow is what we call Newtonian physics, and that's the stuff we've been learning. And then recently, we did this stuff, which was Einstein's relativity, which was things that were big and fast. Now we're in this area and introducing you to a new world of quantum mechanics, and just has a few weird things and different things, and this is one of them, the uncertainty principle. Like I said, you couldn't even talk about that uncertainty principle in the classical physics, but now we see, because of this wave nature, which leads to the uncertainty principle, we cannot know the position of these falling pellets within 1/1,000,000th of the size of an atom. However, that's pretty small. So unless you're dealing with small sizes, so down here, we can pretty much ignore all of this and then just go back and say, yeah, we know the position of this pellet. So in classical physics, we say, this is negligible. We don't count it. We don't think about it. We know for sure that this is the position. But there is always an uncertainty in that position, and it comes into effect only when you get down to the small size, because it results in small things. All right, well, I'll call it quits here. Hopefully that was helpful, and good luck on the other homework problems.